Yeah, let's talk about mathematical induction as one of the slightly less obvious proof techniques or proof strategies, which at the same time can be very powerful, specifically in discrete mathematics and computer science. Induction is all about quantified statements. I've briefly alluded to this earlier, but let's introduce the notation and the notions for that properly. Because this is, again, something that pops up many, many times and is very well worth knowing beyond this module. The first thing we need is statements that have a parameter. So it's basically a placeholder for something, some object, a number in this case. I'll write a of x for a statement that has something to say about this value x. And that could be, from our example, x is an even number. Now, obviously, such a statement can be either true or false depending on the value of x. So it doesn't make sense to say prove a of x, right? I can prove a of 4 or a of 7. But the statement a of x itself, if you want, it's more like a function. For every value of x, it tells you a Boolean value, a truth value, yes or no, true or false. But not by itself, it is it true or false. We can turn it into a logical statement that has a true or false value using these quantifiers. And they basically tell you what you're supposed to do with this variable x. And there's two that are really useful. Existential and universal quantifiers. Existential means there must be some value of x so that a of x is true. There exists some x so that a of x. And we write this with this little reverse e. I don't know where the symbol comes from, but it seems a good mnemonic to say e like exists. Exists x so that a of x holds. And the other one, don't ask me where this symbol comes from, is this little angle. I don't know. Pardon?
Upside down A.
Upside down A. Yeah, that's a good one. Yeah. Okay, like that. Yeah, how could I not miss this? Thanks. Okay, upside down A stands for all. It stands for all. Either way, for all x, a of x should be true. Now you can immediately imagine that that kind of statement is very relevant for algorithms, because we usually want to say they are correct no matter what the input is. That's saying for all inputs, the algorithm does the right thing. And we'll have to talk about the second bit, what that means. So yeah, let's highlight that a bit. These are the statements we very often deal with. As often with these logical statements, it can be convenient to have all of them just to be more expressive, but we could do with just one of them by rewriting. Saying that a is true for all x is the same as saying there's no x so that a is not true, right? I think that's intuitively clear enough. So you could always just use for all or just exists. Now the tricky bit is when we start to nest things. You can have statements that have not just a dependence on one variable x, but on 5 or as many as you wish. And that's where things get really powerful, but also a little complicated. And we have to be careful about the order of the quantifiers. I wanted to put a real example there just to make it clear, even though, okay, I hope that most of you have seen the formal definition of the limit of a function or the limit of a sequence. In this case here, what we're talking about is some function x. It takes a value and it spits out a value. And we could try to prove some properties of that function, like continuity, or is not an analysis class, so don't have to get into this in much more detail. But we want to say as x approaches some specific value, psi is some number that you fix, it's not a variable. As x approaches this value, the function value approaches some other number a. Okay. We'll often use this for asymptotics. We'll see next unit, so not much use to talk about it now. We'll use this full stop. What does this mean that the function has this limiting value? This is one of the things where historically mathematicians played with this for a long while with infinitesimals and trying to do this intuitively. I mean, it's probably fair to say that in some instances they fell flat on their face by not having a rigorous notion for this. And what people came up with as a rigorous notion for the definition of this limit is this, the epsilon delta criterion. It says, you tell me for every epsilon, how close do you want the function value to be to the limit value? You tell me how close you want it. There exists a delta. I can tell you a delta so that if x is closer to xi than delta, the function value is closer to a than epsilon. So nested quantifiers often can be phrased as this kind of game. For all means opponent's choice. You have no control. Exists my choice. I can pick one. Now the tricky bit is the order matters. Having you choose first and I can react to that is different from you choose first, I choose first, and you can react to me. Very obvious in games. Who starts matters. And so for quantifiers, you have to read them left to right. Another way to say this delta is a function of epsilon. It may depend on the choice of the quantifiers to the left. Okay? All right, we won't really talk about limits of continuous functions very much. We'll basically apply this for asymptotics. How does a function or an algorithm behave if n becomes very big? In that sense, we'll use limits. This is more for background and just to make very clear. These quantifiers can be nested, the order matters, and the inner variables can depend on the choice of the outer ones. Okay. Pardon? Sorry, I didn't get that. Yeah, it's the way to build powerful statements. For example, here, okay, let's move on. Simple statements to prove are the existential ones. If you have a statement exists x so that a of x, you just find one x and be merry. That's often simple because you get to choose what the value is. And so it's a simple proof as the ones in the previous subsection. The trickier bit is the for all statements. And that's where we go to the main topic of this section. So let's see how many of you have seen this before. Yep.
For all the negation of an existential.
Yep.
So you can prove it by contradiction. Okay.
Yeah, you can prove it by contradiction.
To prove by contradiction for universal.
Yeah. Okay. So I guess the question would be if I claim for all is hard, why don't we just rewrite as an existential? We could do that, and then we have the negation, so we could do proof by contradiction. The thing is, you would have to prove that any choice leads you to a contradiction, and that any choice, that seems hard, right? Whatever choice you write down, I could say, okay, it failed for your choice, but I have a different one. Maybe it's fine for that one. So you still have this, I have to go through all cases. I don't think you can get rid of that. Induction is a way to get rid of that in a specific sense. You'll see. Good. I think that's enough. A lot of people have seen that. So maybe yeah, maybe I'll do an example, but a quick one then. You'll do an example in the tutorials, but let's first talk about these statements. So we're talking about for all statements. These are the tricky ones. For all x, a of x. And now I'm thinking of x not being any real number, but it has to be something discrete. So the easiest case is natural numbers. Okay? So the statement here has to say something about natural numbers. Yep.
Couldn't you do induction over the view, not like intervals? If you could prove that an interval of a certain size, it made it like instead of if you could show that a party was for an interval, then couldn't you do induction over intervals to prove something over the entire real numbers or something? So that would,
Okay, question is, can we somehow rescue some bits of induction for the reals? I mean, depends. Let's first talk about induction. If the statement is fundamentally about continuous things, then no. But there might be sometimes tricks. I don't know. I think the answer is no. If you can, then you can reformulate the statement. So sometimes we write this restriction as for x in n0 or something like that. So that's, if you want, it's a shorthand for saying for all x, x in the natural numbers implies a of x. Okay. That's logically the same thing. This is more convenient to write. So we often, in a way, this is about mathematicians and types. Often doesn't go well together. Mathematicians are very, very sloppy when it comes to types compared to programmers who are used to the strict typing of most programming languages. So when a mathematician writes for all, it's usually assumed that the reader, the human on the other side, knows or figures out what the possible values for x are. It often doesn't make sense that here x is a square or a motorbike. You usually have a clear notion of what x can be, and it's not a sin to express that implicit thing explicitly. Right? What is the set that x can come from? That said, I'm also sometimes sloppy, and it's convenient to leave things out if you don't have to write as much. So I'll sometimes write things like this as well, in the hope that the range is clear. But it should always be possible to write down the exact range without thinking too hard. What does induction do? Induction does two things. You prove the statement you want to prove for some, sorry, that's not the part of induction. One way to prove a for all x, a of x statement is you prove the statement without assuming something about x. That's sometimes possible. Sometimes it's convenient. I think it's mostly, it's a bit dangerous. Usually you need something about x. So this is in principle possible, sometimes doable, a direct proof. It's a bit dangerous. Induction can be a little more convenient. Yep.
yeah, like something like can prove that x or not x is true for all number values in induction. Like for an arbitrary x or not x is true. You don't have to like use induction to prove something like that. Things that like are contradictions or tautologies.
Yeah, I see. Okay. In some easy cases, when you see that the statement doesn't really depend on x much or something like that. Yeah. Yeah, so that's why I listed it. Sometimes it's doable. Induction is a way when it's not so easy. And there, if we have, say, the natural numbers from 0, we would prove as one thing the statement for 0, and then prove a different for all statement, but one that gives us more ammunition to prove. We prove that for every n, if we have the statement for one number, that implies the statement for the next bigger number. And those two things together are enough to prove the statement for all natural numbers. And people often draw a ladder where you start at 0, you build this first little piece of the ladder, and then you show whenever you can build a ladder up to a certain height, you can get the next higher one by adding one more pole. And so you start with 0 and you prove that you can always make a step. And by always making a step, you get to any fixed height. Okay. That's the principle of induction. In this strict version, you're only allowed to use a of n to prove the next bigger number. This is actually a bit restrictive. You can also just use all previous statements. You use that the statements are true for all values up to the one that you currently look at, and then prove the next bigger one. Sometimes people make a distinction and call this simple induction, weak induction, and this strong induction or complete induction. I don't care too much. It's both induction. There's not too much of a magical difference. You can extend the principle a bit more. We won't really need that here. But you can essentially apply induction whenever something is constructed step by step. You can start from something and then you can make it bigger. And maybe a natural thing for us in computer science and in this module, we'll talk about binary trees. So one way you can apply induction there is you can say a binary tree is a leaf, or it's a node with 2 subtrees, which are binary trees. So that's again a way you can start from one thing and then build up. If you can do that, you can imply induction. Question?
I think the distinction, because, well, in one other set is just basically and a set for which any subset has the smallest value. I think that's like an easier ordered set for which ordered sets for which any subset has the smallest value.
Yep.
Which subset has the smallest value, then that's where ordered sets. Like then I think the distinction between the strong and the weak induction is proving an plus 1 by only from an and proving an plus 1 from multiple previous statements might be different. It might be case that maybe an alone is not sufficient to prove an plus 1. I don't know of any simple examples like that. So like more complicated statement for which more complex sequences for which the next value, if the next value does not depend only on the previous value but on all previous values, we're able to prove it using only the previous value. Right?
Yeah, I think the distinction between this weak induction and the strong induction is a little academic if you want. I think you can reformulate your statement so that it includes all the previous ones, and then formally you apply the other induction if you care so much. I don't think that's the key thing here. What's surprising is that you can basically bootstrap yourself. Inductive proofs, sometimes when you read them, you look like, yeah, I think that's solid, but I've learned nothing about the statement, apart from the fact that you've formally proven it, right? Which is remarkable. Often a proof is assumed to convey a lot of knowledge and insight into what you're proving something about. Inductive proofs need not be like that. They can be completely ugly in the sense they teach you nothing, but they work. And I mean, if the goal of a proof is to prove something, they're really effective. So yeah, sometimes it's much easier to come up with an inductive proof than any other proof. Shall we do a quick example? What are people's thoughts? I guess there's 2/3 that say, don't bother me. I've seen that. And the other third's a bit lost at this point. I'll do a compromise. I'll do an example and run through a little quick so that we can cover the rest. Let's see. I think a nice example is the Towers of Hanoi. I think many will know this. So it's a puzzle. it has some story behind it, but I think this is all made up by mathematicians. And so without, think of your favorite mystical setting, an Indian temple, some Vietnamese thing, or what else? I've read it in a monastery and some hideaway place high up in the mountains or whatever. The game has 3 poles and has disks sorted in size, and the goal is to get the entire pile to a different pole, but you can only move 1 disk at a time, and you're not allowed to ever put a bigger disk on top of a smaller disk. And then usually the story is, well, these priests, monks, whatever, they have to do this, and once they finish, the world comes to an end. And well, whatever. So the most original story I read was that they have 64 pieces stacked on top. And so when they finish this, the world comes to an end. And the question for you is, should we worry, right? So let's try to answer that question. How many steps do we need to move this 64 pile from one pole to the next? If you've seen this before, okay, I know it's maybe has lost its magic. If you see this for the first time, you start playing with 3 or so, and you figure out, yeah, okay, you could do this, right? You can put the top one here, and it's gone from there. Then you can put this one on the other top. Now you're all blocked, but you can get the smaller one from here, put it on top there. And then I can actually move this lower one to the last position. Now I have to think a bit ahead. If I place this here, I can go with that one there. So let's take the smaller to the side, middle one up here, and then finally that one on the top. Good. Easy to do with 3. If you do it with 5, you get already a bit bored and lost, and you move a few pieces around because you messed it up. If you do it with 64, how many pieces? What's the minimal number of steps? Does anyone know? You remember? Minimum number of steps? Pardon? Unfortunately not this time, because, well, we could do first the other. It's hard to spoil I feel for you. It's annoying to spoil a puzzle, but I think I have to. So let's transform that into an inductive statement. We want to say about something for all sizes. It's kind of easier to solve the general than the specific one in this case. So let's say we have n disks. And I'm claiming the number of steps we need if we have n disks is, drum roll, 2 to the n minus 1. And so as a computer scientist, you should know that 2 to the 64 minus 1 is not to worry about. So integer overflows, if you count up in a loop, a 32-bit integer you might see overflow. A 64-bit integer you will never see overflow in this universe. So that's the answer to the very practical side of this puzzle. The poor monks will never finish. I think it's 500 billion years or, well, something like that. Takes basically forever in physical terms. But how would we possibly prove such a statement? By induction. So we would start with the induction base. The base case is, let's be really lazy. Let's say no disks. I have not to do anything, so the answer should be 0. 0 steps are needed. And 2 to the n minus 1, that is 0 if I put in a 0 here. Brilliant. So that's the base case done, right? And now we do the inductive step. which is, I'm assuming, the inductive hypothesis. That's how people often call this. That's the AN. And this is our statement A of n. So let's assume that we already know for n disks, it's exactly 2 to the n minus 1 steps that I need. And now comes the brilliant little insight. If I have my tower, there's one more disk at the bottom, and then a tower of, okay, this is even below my standard of drawing. That's gonna say something. How do we move this pile of disks from here to here? Well, 3 steps. We take this large bit, move it here. That's step 1. Then we move the red part to here. That's step 2. And then we move the gray one back. Easy, right? 1, 2, and 3. How many steps do I need for that? The red one is a single step, easy. The other 2 are the inductive thing with just n, one smaller. So if we start with n plus 1 disks, then the number of steps for n plus 1 disks is 2 times the number of steps for n plus 1. And the rest is arithmetic, because now we can use the inductive hypothesis to replace this by 2 times 2 to the n minus 1. And then you see that this works out to 2 to the n plus 1 minus 1. Right? And that's the end of the proof. You see, in this case, you actually did learn something about the problem, because this is a recursive algorithm, and you could actually implement it by a recursive function just like that. No much thinking needed. But also, see how knowing the solution for the one smaller problem was really all we needed here, and the proof became quite simple. Whereas if you try to prove all of this directly from nothing, it's also doable for this puzzle, but it's more tedious and needs more insight up front, whereas the induction here guided you to what you had to do. All right? Good. That was Towers of Hanoi in 5 minutes. Yep.
Induction to verify the solution.
Yeah.
Is it generally because things that you can verify inductively, you can also discover, like, let's say we didn't know the answer to this solution, not to verify it. Would it have been able to, like, figure out the answer? Would it have been helpful to, like, discover the answer?
Yeah, so that's a good point. So the question is, can you somehow, instead of just using induction for proving what you already know, discover what you want to prove? I think it's the Achilles heel of induction is no, not really. Usually induction doesn't help you discover what you have to prove. Sometimes it can work iteratively. You try with some statement and you try to prove it, and then you see you're stuck, you're missing something. And that can sometimes give you the insight of what that missing bit is, and then you can add it to the statement, and then it goes through, but it's not really like a clear structure. Yep. Induction doesn't really help you much if you don't know what to prove. It can just be super terse and quick if you do.